In this video, I'll be solving problem 815 from Classical Mechanics by Taylor. The problem asks us, in deriving Kepler's third law, we made an approximation based on the fact that the sun's mass, ms, is much greater than that of the planet m. Show that the law should actually read t squared equals 4 pi squared over g ms plus m, that is the total mass of the system, times a to the third, and hence that the constant of proportionality is actually a little different for different planets. Given that the mass of the heaviest planet, Jupiter, is about 2 times 10 to the 27th kilograms, while ms is about 2 times 10 to the 30 kilograms, by what percent would you expect the constant in Kepler's third law to vary among the planets? So, according to Kepler's second law, an orbit sweeps out equal area in equal time, that is, dA dt is a constant equal to the angular momentum over 2 times the mass of the planet if the center of this orbit is fixed, or 2 times the reduced mass in this case. The area of an ellipse is equal to pi AB, and because dA dt is constant, we can say that dA dt equals a over tau, the period. Then tau is equal to a over dA dt, which is equal to pi AB times 2 times the reduced mass over the angular momentum. Okay, now that we've got an expression for the period, we can use the eccentricity of the ellipse to simplify this expression. By 8.53 in the chapter, we have that the ratio between the major and the minor axes is equal to the square root of 1 minus the eccentricity squared. So we can make the substitution that b squared equals a squared times 1 minus epsilon squared, the eccentricity. Then by 8.52, we can also make the substitution a times 1 minus epsilon squared equals c, where c is a constant that is equal to the angular momentum squared over the force constant for the system, which in this case is g m1 m2 times the reduced mass. So first, we'll square the whole original equation. So we have the period squared equals 4 pi squared a squared b squared mu squared over the angular momentum squared. Then we'll make the first substitution for b squared. So t squared equals 4 pi squared a squared times 1 minus epsilon squared mu squared over L squared. I know this doesn't look any better, but it will soon. So now we'll make the substitution for c. T squared equals 4 pi squared a to the third c times mu squared over L squared, and then we'll substitute in the actual value for c. So that's going to be 4 pi squared a to the third L squared mu squared over L squared g m1 m2 mu. So that looks a little unwieldy. Let's do some canceling, and we can also make one more simplification. Recall that mu, the reduced mass, equals m1 m2 over the total mass, which is m1 plus m2. Then mu over m1 m2 equals 1 over the total mass. In this equation, we have mu over m1 m2. So we'll make that substitution, and that gives t squared equals 4 pi squared over g m1 plus m2, the total mass, all times a to the third. So this is the constant term. Now, if we recall that in this system, m1 is the mass of the sun and m2 is the orbiting mass, then t squared equals 4 pi squared over g ms plus m. So now that we've shown that, the second part of the question says, given that the mass of Jupiter is about 2 times 10 to the 27th kilograms, and the sun's mass is about 2 times 10 to the 30 kilograms, by what percent would you expect the constant 4 pi squared over g times the total mass to vary among the planets? The mass of the sun is approximately 1,000 times the mass of Jupiter, meaning that the variation in the total mass is from approximately m sun for a very small orbiting object to approximately 1.001 times the mass of the sun. That's a variation of about 0.1%.